Okay, here's our quick run through for the Unit 4 notes on chemical bonding, where we compare ionic bonding to covalent bonding. First thing we need to do is review our energy levels. So if you remember, around the atom you have the nucleus in the center, you have 3 energy levels. On that first energy level, we can hold up to 2 electrons. On the second energy level, we can hold up to 8, and on the third energy level, we can hold up to 8. When electrons fill, they always fill from lowest to highest energy. And for our purposes, we really only care about those outer energy levels because they're the ones that do the chemistry. Okay, we call that outer energy level the valence energy level. All right. Now, above 3 energy levels, there are more electrons than 8, but because of the way they organize, we still always pattern everything out, basing things on 8. So what are these valence electrons? Well, these valence electrons are those electrons in that outer energy level. They're involved in all the bonding that we're going to be doing, okay? And to be stable, almost all our elements are going to want 8 to fill in that energy level, okay? We have some exceptions, and a few of them only want 2 because they're on the first energy level. And then we already have a group of elements that already have 8, which is our noble gases, okay? So then what do the other elements do to get to 8? Well, they go through bonding, okay, which involves transferring or sharing of electrons. Now, when we do this, we need to know about what's called the octet rule. Because everything wants to have 8 valence electrons, and they're going to chemically react to make that happen, which means they're going to create different bonds. We know this 8 valence electrons is known as the octet rule, oct meaning 8, and that being a rule, okay? So there's 2 ways it happens. We can either transfer electrons, which is basically giving and taking them, and when we do that, we create the ionic bond, okay? So you can look over here, we see one element can transfer an electron to the other element to create the ionic bond, or we can share electrons, which then creates what we call as a molecular bond, and that makes molecules. So we can, instead of having a transfer, we can also have sharing that goes on where they lock together because they share some electrons instead. Okay? And if we're trying to look at these valence electrons and how many each one has, so we can figure out how many get transferred or how many get shared, we can use the periodic table to help us figure that out. So in this slide here, we see all the different energy levels in these different elements, and we're looking for how many valence electrons they have in a pattern. Notice how we exclude the transition metals here because we don't have a great pattern for them. So we're only looking at groups 1, 2, 13, 14, 15, 16, 17, and 18. If we clean this up and only look at the outside electrons instead of all the different energy levels, it would look like this, okay? In this case now, if we look closely, we can see that pattern develop that the Group 1 has 1, Group 2 has 2, Group 3 has 3, Group 14 has 4. So getting rid of the tens place and looking at only the ones place in our group number, that tells us the number of valence electrons. So in group 16, so the 6 means there's 6 of them there. And then we can use a dot structure, these dots, to represent the electrons around the outside of the atom. Okay. Now in class, we set up a whole bunch of rules on how to do this properly. So you'll need to go back to the activity in class to see those rules. So our first bonding type is ionic bonding. And with ionic bonding, we always have a metal bonded to a non-metal. Okay. That's the way we can identify it very quickly. And with metals bonding to non-metals, we're always going to write the metal first, and then the non-metal will be written last. Okay. Again, reminder that ionic bonding is a transfer of electrons from the metal to the non-metal. So the metal is going to give it up, and the non-metal is going to take it, okay? To do this, they both are going to need to have a full energy level of electrons to create that octet rule of equaling 8, okay? This, of course, is going to create some cations for the metals and anions for the non-metals, and then because of that, they're going to attract each other, okay? So when you have a positive charge and a negative charge because of the transfer of electrons, we get attraction. That attraction is what we know as the ionic bond. Now, ionic bonding with this electron transfers, okay, that causes those elements to hold themselves together. So if we look over here, we see sodium giving 1 electron to chlorine. As a result, sodium becomes positively charged, chlorine becomes negatively charged with that extra electron, and sodium has lost an electron. We see how sodium loses its third energy level and drops down to 2 energy levels, which gives it 8. And chlorine also has 8 now around it. Okay? Because it's a positive, because it's a negative, they actually attract each other and they create that ionic bond. Okay? With ionic compounds, this pattern of positive negative repeats itself over and over again to create a crystalline pattern. So we see this repeating kind of structure here, plus, minus, 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 around it. And we get a crystal from that. So here's an example of this crystal structure looking at a picture of it in the macroscopic world. Okay, this repeating pattern we call the crystal lattice of our ionic compounds. Here's a video on forming actually sodium chloride.
A small piece of sodium metal is placed in a flask containing yellow chlorine gas. The flask also contains sand to prevent the heat which will be generated by the reaction from cracking the glass. Initially, no reaction is observed between the sodium and the chlorine. The reaction will be initiated by adding a drop of water to the sodium.
All right, so we see that that white kind of film here is that sodium chloride that is produced in that reaction. And now they make that ionic bond. Here's another video of watching crystals grow. Okay, because of those crystal growth, because of that crystal structure, we get some properties from ionic compounds. All right, first one, they're very hard and they're brittle. They have high melting points, they're solids at room temperature, and they do not conduct electricity when they're in their solid form. Okay, because of this plus-minus repeating pattern, they're going to be locked in a rigid structure, which makes them very hard. But if you hit them hard enough, instead of them sliding and bending like metals can do, when the two pluses get close to each other, they repel and it creates a cracking. Okay, that's what makes them brittle. And again, because they are solid, the ions are fixed in this plus-minus pattern. They cannot move, and if they can't move, we cannot conduct electricity. Now, to conduct electricity, what we can do is dissolve them in water. Okay, so ionic compounds can conduct electricity if you dissolve them into water. Okay, dissolving is going to separate the cations and anions in that solution, and that's going to create free movement of electrons so that they can carry that electric charge. So here's a video of how ionic compounds dissolve in water.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
All right, so when it dissolves, we get minuses and pluses that are now separate, and they're being carried around by these water molecules. So because they're carried by the water molecules and they can now move and flow into the liquid, they now can carry charge. So that's how they conduct electricity. The other type of bonding we have is called molecular bonding. So in molecular bonding, we're going to be reacting nonmetals to nonmetals. And with this nonmetal to nonmetal bond, we're always going to write the least electronegative of the two nonmetals first. And we're going to have a sharing of electrons instead of a transfer now. Okay? Both of the electrons that are part of the sharing are counted by both nonmetals. Okay? So for example, if hydrogen has one electron to share, and this hydrogen has one electron to share, because they're sharing them, both hydrogens are going to assume that they have two electrons so that they have a stable configuration. The sharing of two electrons is considered a single bond. Okay. Now, everything else is going to want to have 8. So if you want a full energy level, or to satisfy that octet rule of 8, you're going to share as many as you need to. So here's 2 oxygens, and each oxygen is going to share 2 pairs of electrons, or a total of 4 electrons. And that's going to give each of them 8. So if we count the outside energy levels, there's 1, 2, 3, 4, 5, 6, 7, 8. Because both the yellow and pink, this oxygen is going to count as being part of it, so it has 8. This oxygen is going to do the same. 1, 2, 3, 4, 5, 6, 7, 8. So it's going to count both of its shared ones for its side too. Okay, so they're going to be sharing those electrons to get to that magic rule of 8. Now, if you share 4 electrons, you get a double bond. If we share 6 electrons, we would get a triple bond. Okay. By doing this, we get small groups of elements bonded together, and we call them molecules. Okay. And then what holds them together is that sharing, and that sharing is called the molecular bond. Okay. Now, molecular bonding, again, next part, because of some properties. All right. Because of the shared between that molecular bond, okay, they are held together to create those molecules. So we have hydrogen here and oxygen. If they come in and share, we have hydrogen sharing an electron with oxygen. Here it's sharing an electron with oxygen, creating a covalent or molecular bond, or water. Here's how you can see it in the dot structure. So in this case, the hydrogen is sharing and sharing. You see how the oxygen has 8 around it, and both hydrogens have 2 around it. Now, instead of putting dots for those shared bonds, usually we draw those as a single line like this. So you'll see that line to represent that instead. This does not create a repeating pattern, and without a repeating pattern, we don't get a crystal structure. Okay. Now, the molecular bonds are only between atoms in the molecule. So we get molecular bonds inside this molecule, inside this molecule, inside this molecule. But there's no bond between them, so there's no crystalline structure that forms. There is an attraction between them, and that attraction we see is called an intermolecular force. Okay? So when we write up these shared electrons, instead of putting a bunch of dots in here, we change them to lines. So each line represents one shared pair of electrons. So this carbon is sharing 2 electrons, 4 electrons, 6 electrons, 8 electrons. This oxygen is sharing 1, 2, 3, 4 electrons with that carbon. Okay. In this case, there's 2 electrons being shared in each one of these bonds here. Okay. That's where those bars or lines come from. Now, what holds one molecule to the next? So like what keeps this water molecule attracted to this molecule? There's something called IMF, or intermolecular forces. Okay, they're a weak force, and they go between 2 molecules. Okay, and that holds those molecules together. Okay, instead of using a solid line for that, we use a dotted line to represent that. Okay, they're not part of the molecule; they're between them. Okay, we still need to have an attraction between things, otherwise we'd all be gases, and there would be nothing in their liquid form, which we know we can create. Now, because of the fact there's no crystalline structure, we end up with some new properties for molecules. Molecules are softer than ionic compounds. They're less likely to be brittle, so they're more likely to be flexible. They have a low melting point, which means that they can be solid, liquid, or even gas at room temperature. Okay? They do not conduct electricity as a solid. Okay? In fact, they don't conduct electricity in any shape or form, okay, as we do this. Because of the fact that they don't form any ions, they do not conduct electricity in any state. They don't break into ions in solution. They do separate by molecules, so we don't break the ionic bond, we break those IMF, or intermolecular forces, so each group floats away with the water molecules when they're dissolved. So when you're dissolving something like sugar, these are all sugar molecules here, these big kind of globular things. They still dissolve, but they stick together and they don't break into separate ions. So if they don't break into separate ions, there is no charge, and if there is no charge, then there is no way to conduct electricity. Okay? So you need to have moving ions. So with no moving ions, there's no electrical conduction inside there. Okay? As a result, we get these comparisons. So we can take a look, and you can pause the video and look at the comparison between all these different things between ionic compounds and molecules. Thank you.